All right. So for the most part, people did really well on the top section with just like the intersection, union, difference, symmetric difference, complement, no problem. It's then when we got into the power set that was a little bit tricky. Most people did pretty well with that one, but there's just a little notation here and there that we need to fix up. And then this section was a disaster. So we need to talk about the difference between subset and element, okay, because that was pretty disastrous. So I'm not going to go over these. If you have individual questions, just let me know. Come see me, see the TA. Most people didn't have trouble with that. Okay, so remember, when we're talking about a power set, we're talking about all the possible subsets. Okay, and so remember that so this is the empty set. That is the notation for it. It's also the same thing as this. Okay. Oh, yeah, sorry. So some of you might want to just go to this notation instead if it's helpful. Okay. And I'm going to do that for this first one. Okay, I'm going to write it two different ways just so I think that it will maybe help you. All right. So the power set is a set, so I'm going to put little brackets here, of all the possible subsets. Okay. So first, we have subsets of size 0. There's nothing in them. So that's like this. So you could put that like this, or you could put this. Okay. But what you can't put is that, because that is not a subset of size 0. That is a subset of size 1. Okay. So this one is not correct. It can't have little brackets around it. So you can put nothing between the brackets, if that's helpful, or you can list it as the empty set. Those are just the same thing. Okay, but so those would be all the subsets of size 0 that have nothing in them. And then we have to have another set. Okay, so some of you just put that 1 and then 2. 1 is not a set. That is an integer. Okay, if I want to make it a set, I've got to put brackets around it. Okay, now that is the set containing the integer 1. And this is the integer containing the set containing the integer 2. So now I've got all of the subsets of size 0, all of the subsets of size 1, and then I can also have a subset of size 2 because there's 2 things in the set. Oops, sorry, this was a 6. And then the last one would have both 1 and 6 in it. Okay, so notice these brackets match up. I've got a set, and there's 4 things in it. 1 set that has nothing, 2 sets that have 1 thing, and 1 set that has 2 things. This had cardinality 2. We're expecting to have 4 elements, 2 squared in it, and we do. Okay, so most people did these ones okay. It was this thing. Okay, some people wanted to put a set containing the empty set. Okay. All right, then we get down here. What is the difference between this little symbol right here? It looks kind of like an E for element. That means is an element of. Is an element of. So that's the way you read that. And then this one right here, that's the subset. Is a subset of. Okay. So if I'm looking for this one, is an element, I need to look at what appears on the left side of that operator and see if I go to the set, is it in there? Okay, most of you did this correctly. Let's see. A intersect B, it has, let's see, they both have 3 and 7 and 8. Okay. And so I can look, all right, 1, is that an element of this set? So I go to this set. 3 is an element, 7 is an element, 8 is an element. 1 is not an element, so this would be false. Okay, it is not an element of that set. Okay. This one, this symbol right here means is a subset of. Okay, and that operator works on 2 sets. I have to have a set on the left, and I have to have a set on the right. And then I ask myself, is every element of the set on the left also an element of the set on the right? Okay, that's how I should be thinking about it. So when I go to this one right here, 1, is that a set? It's not even a set. This is really kind of like a nonsensical kind of statement. Like, of course, the number 1 is not a subset of anything because this isn't even a set. Okay, so it doesn't even make any sense. It's not a set. So this is obviously false because the thing on the left side of the operator isn't even a set. Okay. Then for 1, is that an element of A minus B? What was A minus B? 1, 4, 5, 9. Okay, so this time we're asking ourselves, okay, is that an element? Okay, does that appear as an element in this set? Yes, it appears right there, so this one would be true. Okay, okay. This one, notice it's very similar. These look very much the same, but there's the little line under is missing. So this is a proper subset. Okay. So that means are all the elements in this set also in this set, and they're not the same set. They can't be equal to be a proper subset. It has to be completely contained, and there has to be extra stuff in this set over here. So if we look at A intersect C, 6 isn't in common, so this set is also 1. So is a set containing 1 a proper subset of the set containing 1? No, it's not, because they're equal. Okay. If there were a little line under and it was just subset, then it would have been true. But because it's proper subset, it's false. Okay. Then this one, this is an element. Okay. Do I see a set containing 1 as one of the elements in the power set? So if I go over here, there are 4 elements in the set, and indeed, the set containing 1 is one of the elements. So this one is true. Okay. That is different from subset. So this one says, are all the elements in the set on the left, do they appear in the set on the right? Well, what are all the elements in this set? 1. That's the only one. So the first element and the only element is 1, and I go, look, is 1 in there? Nope, 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 nope. Containing 1. Okay, it's not the same thing as 1. So no, this is not a subset because this element is not in this set, so this one is false. Okay. Is the empty set an element of the set A? If I go to the set A, okay, it's got 1, 2, 3, 4, 5, 6, 7 elements, and none of them are the empty set. Okay, so no, it is not an element of that set. Okay. Is the empty set a subset of B, a proper subset of B? Okay, so this is where you might want to think of that, well, this is really like, another way to write that is this. So I look between the little brackets, and is everything that I see in there in here? Well, there's nothing in there, so sure. Right? So everything that I see between the brackets, which is nothing, there's nothing to check. So this one is automatically true. Okay, as long as it's not equal, and that's B is not the empty set, it's not equal, so that one's true. Okay. Is the empty set an element in the power set of C? Okay, so I go, is it one of the 4 elements? Yes, it's that one. Okay, so yes, it does appear in there. Is the set containing the empty set a subset of the power set of C? So I have to go through this set, and everything that I find in this set, I have to look for it and see if it's in there. Okay, so there's only one thing in this set, that's the empty set. Is that an element in here? Yes, it is. So this one is also true. Okay. Questions? Yes. 12 and 16. Yes. Okay. So for subset, I need to look at the set on the left, and I need to systematically go through all of the elements in that set and see if every single one of them appears in this set. Okay. So here's a set, okay, and there's only one element in it, the integer 1. Okay. So I need to go look for the integer 1 in this set and see if it appears in there. Is this the integer 1? No. Is this the integer 1? That's the set containing the integer 1, okay, but it's not 1. Right. So they have to be exactly the same, because an integer and a set are 2 different kinds of things, right? So this is a set, this is an integer. Okay. So, yeah. So that's not 1, that's not 1, that's not 1. None of them are integers. They're all sets. So it's not in there.
To kind of make it a little easier, could you, like, with 12, could you also write it how you have number 8? Kind of say like, oh, like, it's just like the actual number 1. Because that's really what number 12 is saying, right? It's like the set of 1 that has an element of 1.
Well, what this one is really asking you is 1 an element of the power set of C? Because that's the only thing, that's the only element in this set. Now, if I had more elements in this set, I would have to go through all the elements and ask myself. But that's what it's asking me, really. Okay? And so, no, 1 is not an element of the power set. It's got 4 elements, and none of them are the number 1. Okay? But I don't think of it as writing it like number 8, because 8 doesn't make any sense. This isn't a set. It's more like writing it like number 7. It's asking, like, is the thing in this set an element of that one?
Gotcha.
Yeah. Okay. And then number 16 is very similar. So number 16, I've got a set, and I need to go through all the elements in that set and check and see if they're in the power set. There's only one element in that set. That's the empty set. So I go and check. Well, is that element, the empty set, one of the elements of this one? Well, yes, it is. It's right here. Okay. And so, yes, all of the elements in this set are also in the power set. Other questions? Yes?
What's the main difference between a subset and a proper subset?
So the difference between subset and proper subset is a proper subset cannot be equal. The things on each side can't be equal to each other. Yeah. So it means it's like completely contained, and there's actually extra stuff in the set above and beyond. So if they're equal, it's not a proper subset. They're actually the same set. Okay. So with subset, every set is allowed to be a subset of itself, but it can't be a proper subset of itself. Okay, and then I think most people did pretty well. You remember that the cardinality of the power set is 2 to however the cardinality of A. There were 7 elements in there, so this was 2 to the 7th or 128. A couple of people accidentally forgot that when you have numbers from 0 to 10, that's 11 different numbers. So some people did 10 minus however number in B instead of 11 minus in B. Okay. If you rewrite this as the empty set, the cardinality of that is how many things are in that set. There's nothing in there, so that's 0. And now the intersection, okay, here's one element, the empty set, and I need to see, okay, what is that a common element to the power set? Yes. Okay. Both of those have that element. Okay, so the intersection of these two sets is also going to be a set, and the only element they have in common is the empty set. Okay, so that's what I'm taking the cardinality of. That set has exactly one element in it, the empty set, so that would have cardinality of 1. And y'all got pretty good at drawing little curly braces. You have to draw lots and lots of them. All right. Is that better? Keep working on it. Yeah. Hopefully it's better. But all right. You see, let me go over the last. I hope that's where we left off. It's the last page I had. All right. So we are picking up with our discussion of proofs, and we're actually going to get to write some proofs today, so I'm super excited. Writing proofs is one of my favorite things to do in all the world. Okay. All right, so first we want to talk about an idea of, so I think we had talked about a proof by exhaustion last time, where if you have a small domain, you could go through every single thing in the domain and check and see if the thing that you're trying to prove is true. Now, as you can imagine, that's usually not a very realistic thing to do, especially if you're talking about an infinite domain like the set of integers or like the set of real numbers or even the set of rational numbers, anything like that. Like you can't go through every single possible one. It's because there's an infinite number of them. Okay, but even if the domain is just really large, and especially if it's infinite, it's a proof by exhaustion is either impractical or impossible. Okay, and so we have to be able to make some kind of a general argument about an infinite number of things often without actually examining an infinite number of things. And to do that, a proof has to use something called universal generalization to prove a universal statement. And the way what you're doing there is you're just saying, I'm going to pick an arbitrary object in this large domain or this infinite domain. And because it's arbitrary, everything in the domain shares its characteristics. And I'm not talking about a specific number, I'm just talking about an arbitrary one. So anything I say about that arbitrary object applies to everything in the entire domain. And so if I can prove that this thing is true about this arbitrary object, it will apply to every single thing in the domain. Okay, so this is the idea of universal generalization. I just pick an arbitrary object, and then I can make a general argument about this arbitrary object that applies to everything in the domain. Okay. So for example, this sum of two even integers is even. Okay. This is not going to be a super formal proof. We'll get to those later on. But with what we've seen so far, if we wanted to show that the sum of two even integers is even, the first thing we would do is we would want to do this sort of universal generalization. And we would say, let x and y be arbitrary even integers. So there, just when I say that they're arbitrary, this is my universal generalization. Okay. So there's nothing special. It's not 2, it's not 8, it's not 16. They're just any even integers. Okay? And I'm not saying exactly which ones they are, so that whatever I say about them can be applied to every single even integer that exists. Okay. Well, we know, and we would say something like, well, by the definition of even, okay, there exist, okay, integers j and k such that, okay, well, x equals 2 times j and y equals 2 times k. Because that's the definition of even. We went over that last time. If we did the definition of even, like if an integer is even, then there exists an integer such that x can be written as 2 times that integer. Okay, so these aren't necessarily the same integers, right? They have to be arbitrary, so we can't force them both to be the same integer. They have to be two different integers. They could be the same if j and k are equal, but they don't have to be. Okay, but we know because they're even that we can write them as 2 times another integer, both of them. Okay, and we're trying to prove something about the sum of those two numbers. Okay, so we could say, well, the sum x plus y is, well, that's 2j plus 2k. Well, then, if we factor the 2 out of this, we could rewrite that as 2 times j plus k. And we're trying to show that x plus y is an even integer. Well, remember that an integer is even if I can write it as 2 times some other integer. So our question is, well, is this an integer? Okay. Well, we know j plus k is an integer because the set of integers is closed under addition. Okay, remember we talked about closure properties last time, and the integers are closed under addition, subtraction, and multiplication. That means if you ever take any integers and you perform those operations, anything that involves multiplication, addition, and subtraction, you'll get an integer back. Not division, but multiplication, subtraction, or addition. Okay, and so now, since this is written in the form 2 times an integer, okay, so x plus y is even by definition. And we could even put our little fancy box under there. Okay. And so we didn't pick any specific integers. We weren't talking about any. We're just, this applies to any integer. This applies to any integer. We add them together. It's a very general argument. And now I know it's true for an infinite number of even integers, even without having to consider, you know, okay, is 2 plus 2 even? Yeah, it is. Is 2 plus 8 even? Yeah, it is. Like, obviously, you couldn't go through all of them. So this is the way to argue it, just in a general way. Okay. So if we want to disprove a universal statement, that's much easier than proving one. So we can't prove a universal statement by just providing a single example, or even a list of several examples. There's no such thing as proof by example for a universal statement. Many people have tried to do it, but it never works. So I'll save you the trouble. Don't try to do proof by example for a universal statement. Okay, so this is what you should not do. If I'm supposed to, if let's say we wanted to try to prove that n plus 1 squared is greater than n cubed. We kind of looked at this example last time, and we could say, okay, well, let's just start thinking about it. Well, when n is equal to 1, I would have 1 plus 1 squared, that's 4, and that's greater than 1 cubed. That works. When n equals 2, 2 plus 1 squared, that's 9. That's greater than 2 cubed. That works. Okay, I think last time we did 0 and greater. And then 0 plus 1 squared is 1. That's greater than 0 cubed. That one works. You say, hey, it worked like 3 times in a row. Like, this is definitely true. Yeah. So, okay. So it worked 3 times in a row. It must be true, right? What do you think? Wrong. It's not. Okay, so just because I got it to work 3 times doesn't mean it's going to work the next time. Okay, so a statement like this, okay, so I got it to work 3 times in a row, but if I want to disprove a universal statement, remember a universal statement says that this is always true, no matter what value of n I choose. Okay, so if I can just find one that doesn't work, then I've just disproved it because it's not true for all of them. Okay, so if I kept going and I went down here to n equals 3, well, 3 plus 1 squared is 16. Is that greater than 3 cubed? No, because 16 is not greater than 27. Okay, and I just found a counterexample. So even if it works 3 times, it doesn't mean it always works. Okay, once you get to 3 and beyond, it's not going to be true, in fact. Okay, so you cannot prove a statement by using 1 example, or 2 examples, or 3 examples, or 10 examples, or 27 examples, or 112 examples. Okay, I don't care how many examples it is. You maybe have a conjecture, something that you think might be true, but you haven't proven it until you've made a general argument that shows that it's always true for an arbitrary element. Okay. So, disproving a universal statement, you can disprove something with a single example. You cannot prove it with a single example. Okay. Okay. And most of the things that we will be proving are written as conditional statements, like if this, then that. Okay. And sometimes even if they're not written that way, okay, that's if you look at them, you can turn them into that. Okay. So you should always think of the thing, any kind of theorem or thing that you're proving as an if-then statement. If this hypothesis, then these conclusions. Okay. So we know from our work in logic that if we want to disprove a conditional statement, okay, a theorem written as a conditional statement, we would just need to find a counterexample that makes the hypothesis true and the conclusion false. That's the only time that we get a false conditional. Okay. So this is one of my favorite things. My geometry students, okay, I ask them, what's the Pythagorean theorem? And they tell me that the Pythagorean theorem is a squared plus b squared equals c squared. That is not the Pythagorean theorem, okay? Because if you just write a squared plus b squared equals c squared, that means, if you just look at that, for all a, b, and c, for every, okay, a squared plus b squared equals c squared. Okay, can every positive integer be expressed as the sum of the squares of two integers? For every single, like, 3. Can you find an a squared plus a b squared equals c squared for if c was like 3? No, you couldn't. Okay. Okay, so like we can find lots and lots of counterexamples. Okay, we'll just do a equals 1, b equals 2, c equals 3. Is 1 squared plus 2 squared equal to 3 squared? No, it's not. Okay, so that is not the theorem. The theorem is if a and b are the legs of a right triangle and c is the hypotenuse of that triangle, then a squared plus b squared equals c squared. There's a very important hypothesis there of the way that you're choosing the a, b, and c. It's not just this general statement that it's always true no matter what. Yes?
This is probably off topic. Why is it considered a theorem, like Pythagoras' theorem? Why is it in a law? Is there a counterexample to it?
It's a theorem because it's mathematically proved. So yeah, so I don't. Yeah, so why we have laws? I don't know why we don't call the laws
It hasn't failed me once, so I don't see why it is a law.
Yeah. So laws generally tend to be reserved for scientific things, the universal law of gravitation, or where scientific things that actually can't be proven. They can only be tested, and nobody has ever. But you know how the science is. For a while, it was. They thought that the Earth was the center of the universe, and they worked under that assumption for many, many years. They thought the Earth was flat. Then they found, oh shoot, it's actually not, and then it changes. And science is changing all the time. So things that are tested and proven are tested and haven't been disproven tend to be laws in science, and usually we call them theorems in math. But you're why is it
So it's just
De
a
Morgan's
choice of vocab.
law? Yeah.
I was curious because it kind of didn't make as much sense to me.
Yeah, I don't know why we don't call it De Morgan's theorem instead of De Morgan's law.
Yeah.
I would have called it a theorem, but I guess I didn't choose it. But yeah, I see what you're saying. It seems,
Confusing vocab.
yeah, I feel like it should be a theorem as well. Because in general, theorems are things that can be mathematically proven, whereas laws are more like scientific things where they're tested and no one's found something that goes against it, but that sometimes they're changing and tweaking it, and yeah. All right. So I don't know. We're still I'll try to look into that and see if I can figure out why it's called a law, but I don't.
That'd be cool.
Yeah. That is an excellent question because I'm not sure. It seems like a theorem to me too. Okay, so we've just been talking about universal statements. Then we've got existential statements. So a proof that shows an existential statement is true is called an existence proof. The most common kind is a constructive proof. Okay, so if we have a statement like, there exists an X such that this is true, like the first thing you, like, I don't know, maybe you guys are too young to, did you ever watch the movie that had the show me the money in it? Like, no, you're too young. Okay, so, sorry, I'm just old. Okay. Like Tom Cruise was in that movie. I'm trying to remember what the name of it was. I can't remember. Anyway, so the idea here is like, oh yeah, it exists, well show it to me. Okay, so that's what a constructive proof is, where we say there exists an X such that this thing is true, and then, okay, a constructive proof would actually show you the X, okay, that it's true for, or an X that it's true for. Okay, whereas a non-constructive proof is a little bit more esoteric, and it doesn't actually show you a specific one, it just makes some kind of general argument that that kind of a thing could exist. It doesn't give you a specific example, it doesn't tell you what it is, it just tells you that it could exist. We're not going to do any like this, that's sort of for more advanced math classes. All of ours are going to be constructive proofs, where you actually come up with a specific example of something. Okay. So, for example, there are integers x and y such that x plus y squared equals x squared plus y squared. So that is, you see there are, this is an existence. Okay, this is an existential statement. So if I want to prove this, then I should be able to either do a constructive proof where I find x and y that makes this true, or if I can't find an x and y that makes this true, then I would have to do some kind of non-constructive proof and argue that this could happen without telling you what they are. Okay, but probably you can find examples. So can you find an x and y that would make this thing true? Yes?
Wait, no, never mind. Actually, 0?
Okay, so
It's not an integer.
x equals 0, and what do you want y to be?
Y can equal 0 too.
Okay, good. X and y can both be 0. One of them has to be 0 for it to be true. Okay, so, but sure, let's make them both 0, and then we can't go wrong. So, 0 plus 0 squared, okay, and 0 squared plus 0 squared. Indeed, those are both 0. It works. Okay, so I can prove this, okay, is true by constructively showing you a specific example that makes it true. Okay, so does that mean that since I found this example, does that mean that x plus y squared equals x squared plus y squared? Absolutely not. Okay. Okay. This is a favorite algebra blunder that I teach algebra. I think I told you, and I see this I write this on my students' papers all the time, because they do it all the time. Okay, but we know that x plus y squared is x squared plus 2xy plus y squared. Okay, and the only reason that it worked out here is because one of x or y are 0, and that middle term dropped out. Okay, but if one of them isn't 0, it doesn't work. Okay. So this is an existential statement written like this, just x plus y squared equals x squared plus y squared. This, because there's no quantifier specified, we will always assume that it's a universal statement. So this is a universal statement. Unless we add something like there are in front of it. Okay, if I just write it out like this, I automatically assume that it's a universal statement. Okay, and we know that that's not true. Okay, so disproving an existential statement. Okay, so remember that an existential statement asserts that there's at least one. So if you want to prove it, you just have to find one. Okay, but if you want to show that it's false, think about the fact. So there exists an x such that p of x. If I want to show that that's false, then you have to show that the negation of this is true. So you have to show that for all x, not p of x is true. Okay, and that's a much harder thing to do, because now that's a universal, and I have to make a general argument about the entire domain and show that if I go through the entire domain, I can never find a single x that makes this true. Okay. So, proving an existential statement is easy, disproving it is hard. Okay, just the opposite thing for universal. Proving a universal is hard, disproving it is easy. All you need is one counterexample. Okay. For an existential, to prove it, all you need is one example. Disproving it is hard because you have to consider the whole entire domain. Okay. So, for example, if we wanted to disprove this statement, there exists a negative integer that is equal to its square. Okay. Okay. So if you think about that, okay, so there exists a negative integer, so x would have to be a negative integer, and then the predicate here that integer square is equal to its square. So, for example, the positive integer 1, if I square that, that's 1. It's equal to its square. Is there a negative integer for which that is true? No. So there's no possible way. So if I want to disprove that, I would have to show that there doesn't exist a single integer. But we can make a general argument. If I have a negative integer, okay, so a negative integer times a negative integer equals a positive. Okay. This positive cannot be equal to the original negative. Okay. That's a very intuitive, non-rigorous proof, but I mean, you'd have to make a general argument. I have an arbitrary negative number, okay, and I multiply that arbitrary negative number times itself. I will always get a positive product. That positive product cannot possibly be equal to the original number, which was negative, because a positive number and a negative number are never equal. Okay. But you can see that it's a general argument, and we have to think about arbitrary things from the domain. We can't just come up with an example. Okay. So before we write proofs, we're just going to quickly go through a couple of these best practices that the book points out. Okay, so when we are writing proofs, we all have to agree that there are certain things we're allowed to use and certain things that we're not allowed to use. Okay, so we are allowed to use all the rules of algebra that we know. So you can use any of the commutative, associative, distributive laws, any properties of equality like addition property of equality and subtraction, like just factoring, anything from algebra. Okay, so you can use anything from algebra that you know. Okay. You may use the closure properties of integers that we've talked about. So this set of integers is closed under addition, subtraction, multiplication. Remember, it's not closed under division. If I take two arbitrary integers and divide them, I might not get an integer back. Like 1 divided by 2 is not an integer. 2 divided by 3 is not an integer. Okay. This is called like the well-ordering principle. So if I've got x and it's an integer, then there's no integer between x and x plus 1. Okay, I have x and x plus 1. That's the next one in line, and there's no integers in between there. Okay. So we also call these consecutive integers. So that's how we would find consecutive integers, x, and then add 1 to it to get to the next one. Okay. You're allowed to use, the ordering of real numbers. Like that 2.5 is less than 4.3. Like you can use any kind of inequalities that you know from the set of real numbers, integers, anything that's real. Okay. We also can use that the square of a real number is non-negative. Okay. Notice it's not positive, it's non-negative, because a square of a real number could also be 0. So notice things that we didn't say here. So we didn't say closure properties of rational numbers. You're not allowed to assume those. Many of the proofs that they ask you to do are about rational numbers. And so you can't use the closure properties of real numbers. You can only use of rational numbers. You can only use closure properties of integers. Okay, so integers is listed here. Okay, not rationals. You're not allowed to use those. Okay. Okay. I'll try to write a few different orders and proofs so that you can get some different ideas and you'll come up with your own of how you like to write them. But in general, okay, you would like to indicate where the proof starts and where it ends. So, like in your book, they like to just put the word proof, colon, to let everybody know, hey, we're starting now. And then when it ends, you can put your little colored in square at the bottom, or you can put a QED, whatever you like, but so that we know when you started and when you end, and hey, we're done now. Okay, so you should in general write incomplete sentences. Okay, give the rotor a read map. Give the reader a road map. So say what you're assuming, what you've shown, sort of sometimes where you're going, so a person that's reading along can figure out what's going on. Okay, I'll do that for you. So if you follow the examples the way I do them, then we'll do so many of them that you'll get an idea of what kinds of things to put in them. Okay. You should introduce any variable when you're using it for the first time. So don't just start using something and you haven't defined it yet. Okay. And then it's really tempting to just write a bunch of math. Okay, but that sometimes is really hard to read if you don't have some nice English text logically separating the math that you're doing. Again, I'll put some sentences in there. I'll show you where it's a good idea to put some English text in between some of the math and algebra so that we can easily follow it. Okay. So let's So we talked about universal generalization. There's also an existential instantiation. That's sort of similar in nature to that. So if you have a there exists kinds of statement, so this existential instantiation is just a law that says if we know that an object exists, you can give it a name. So if, like in a definition of, a number is even if there exists an integer such that you can write y equals 2 times that integer. So I know that thing exists, so I can just give it a name so we can talk about it. So I can say, like, let that integer be called k. I know it exists, so I'm going to give it a name. I'm going to call it k. Okay. So here's our example. If we know there's an even number, we can give that number a name, n. Furthermore, since we know that all even numbers are multiples of 2, we can say that n equals 2k, and we can give that integer that exists a name. And now it's much easier for us to talk about that even integer, okay? Because we know that another way to talk about n is to call it 2k, and so it makes it easy for us to talk about and make arguments about it using mathematical rigor. Okay, so here, if we have, let's say this proof, if n is an odd integer, then 4 divides n squared minus 1. Let's say that's what we want to prove. So let's do an example of what a proof might look like for this. So remember, we want to say where it starts and where it ends. Okay, so we would be like, proof. Okay, and everyone knows that I'm going to start it now. Okay, so think about that this is the hypothesis, and this is the conclusion. Okay. So the other thing we're supposed to do is make sure that we're stating any assumptions we make. Well, when we're proving this, we're assuming that the hypothesis is true. And we're trying to show that if the hypothesis is true, then the conclusion will be true. Okay. So we would say, assume that n is an arbitrary odd integer. Okay, so there is our assumption, our universal generalization, right? That's what that statement is. This is the universal generalization, states our assumption. Okay. And then you probably want to say what you're going to prove. Okay. So here I would say we will show that 4 divides n squared minus 1. So state what you're going to prove. Okay. And that way, at the end, when we get to a point where we say, so 4 divides n squared minus 1, now we all know that we're done, because I already told you right up front, this is what I'm trying to show you. Okay. So I have a statement. Basically, I'll just state that I'm assuming my hypothesis is true, and I'm going to show that my conclusion is true. Okay, so this is going to be the conclusion, right? This assumption, this will be our hypothesis. Sometimes we have more than one. Okay. And so now we just argue from things that we know or assume to be true. So what I know that is true is n is an arbitrary odd integer. Well, if I can say, all right, well, what can I use? Well, if n is an arbitrary odd integer, I know what the definition of odd integer is. So I know that there exists, like a k such that n has to be equal to 2k plus 1. So I know that that's the definition. So that's probably where I want to go from there. So what can I conclude to be true because I know that n is an arbitrary odd integer? Okay, so I might say then, by definition of odd, okay, we know, there exists a k that's an integer such that, okay, if you want to abbreviate, you may do that. Okay, this stands for such that, okay, and then we know that n has to be 2k plus 1. Okay, so here I'm just using the definition to make a valid conclusion. All right, and then I go, okay, well, where am I trying to get to? What I'm trying to show is that 4 divides n squared minus 1. So you might ask yourself, well, I wonder what n squared minus 1 is. Well, I know what n is, so I should be able to figure out what n squared minus 1 is. Okay. So maybe substituting this expression into n squared minus 1 yields, what a fun word. Okay, n squared minus 1 equals 2k plus 1 squared minus 1. And then I can do a little bit of algebra on it. Okay, well, 2k squared, or 2k plus 1 squared, well, that would be 4k squared plus 4k plus 1, and then minus 1. And if I simplify that, I'm just going to get 4k squared plus 4k. Okay, so all of this, I can use algebra to make valid conclusions. Yes. Okay. And then we think about where I'm going. Well, I'm trying to show that 4 divides n squared minus 1. Well, here I have n squared minus 1. I know it's equal to this expression. Okay, and I see all these juicy 4s in here, right? And so I feel like I just really want to factor out that 4. Okay. And then I think about the definition for divides. Well, I know that x divides y if y can be written as some integer multiple of x. Okay, so 4 would divide n squared minus 1 if it could be written as some integer multiple of 4. And we just wrote it that way. Okay, and so we might then say, oh, I should have used a different letter, so because k is from your definition, but that's okay. So let's say we'll call it m equal k squared plus k. Well, we know that m is an integer, okay, because we did multiplication here, we did addition here. on an integer. Okay, so we know that that also has to be an integer, okay, because the set of integers is closed under multiplication and addition. So here we're using closure properties to make valid conclusions. Okay. And so then maybe we'd say since n squared minus 1 equals 4m, n squared minus 1, or sorry, 4 divides n squared minus 1 by definition of divides. So here I'm just using a definition again. Okay, and as soon as I get to this, which is what I said I was going to do up here, then I know I'm done, and so then I can put a very little satisfying kind of end mark so everyone knows that I'm done. Okay, so that would be what the whole proof looks like. So I've marked my beginning and my end. I've said my assumptions. I kind of gave a little roadmap. And I've only used the valid things that we all agreed that we're allowed to use, like definitions, algebra, closure properties of integers, just of integers, to make an argument to prove what I'm trying to prove. Okay. So that's a great example of how you might go about writing a proof. All right. So common errors that we might make are trying to generalize from examples. Hey, look, it works for 2, and it works for 3, and it works for 4. It must work for everything. No, you cannot just do a couple examples and then assume that it always works. So don't try to generalize from examples. It doesn't matter how many examples you show it's true for. That doesn't prove that it's always true. Okay. Lots of people want to skip steps. Okay, they might want to say, well, n is an odd integer, so n equals 2k plus 1 for some k. Therefore, n squared equals 2k plus 1 squared. So n squared is an odd integer. Well, I never showed that it met the definition. I can't just make a claim like this. There's too much hand waving. That's not a convincing argument. How do you know that n squared is odd? Can you write it as 2k plus 1? That's the only way I know it's odd. So don't try to skip steps and wave your hands and say, well, it's probably true. I mean, they told me to prove it. I'm sure it must be true. You can't. You got to actually go through all the steps to get to using definitions for if you're trying to prove divides or rational or odd or even, anything like that. Okay. Circular reasoning is when you're using the statement that you're trying to prove in the proof itself. So, for example, if you were trying to prove that the sum of 2 even integers is always even, and then at some point in your proof, you're like, well, this is even and this is even, and so the sum must be even because whenever you add 2 even numbers, you get an even number. That's what you're trying to prove. You can't use that in the proof. That's circular reasoning. So you cannot use the statement you're trying to prove in your proof. Okay. And assuming facts that have not yet been proven. For example, okay, we have not proven the closure properties of rational numbers, so you can't assume those. Okay, we have to only use the closure properties of integers, not of rational numbers. Okay. So the first and easiest kind of proofs that we're going to do are direct proofs. These will be on the exam that is on Tuesday the 18th. Okay, just before we start this, just a little, so we have homework from section 3.1 I may do tomorrow because I didn't announce it in class last time, so it's due tomorrow by 5. So if you haven't done that yet, I know some of you have, but if you have not yet done that, homework for 3.1 will be tomorrow by 5. And then up through section 3.4 is going to be due on Thursday before class, so when we come back after the break. So a week from today, up through section 3.4. And then, of course, we have the exam the following Tuesday. I already put a study guide, a review sheet of the things. There's quite a bit on there. So, try to look at that before you come to class next Thursday. So if you have any questions, we can go over them. Okay. So, theorems to be proved can be written as conditional statements. In fact, even if they're not, you should write them out as conditional statements so that you can easily see what the hypothesis and what the conclusion is. That'll help you say what your assumptions are and what you're trying to prove. Okay. So, in a direct proof, which is what I just did on the previous one, we always assume that hypothesis is true, and then we use any kind of valid argument that we can to prove that the conclusion is a result of the assumptions. Okay. So we're always going to state the assumptions that we make, just like I did in the last example, that whatever the hypothesis is true. State what you're trying to prove. Basically, you're stating the conclusion. Okay. And then you can use any kind of definitions, theorems, things that you've proved before, okay, to derive what the conclusion that you're trying to prove. All right. So we'll just try to get through as many of these as we can. So we want to prove that the product of two odd integers is odd. Okay. All right. So if we had to write this out as an if-then statement, it's not really written then as one, right? But if you think about it, what we're saying if, okay, x and y are odd, then x times y is odd. Okay, so at least have that idea in your brain. This is what we're doing. If this, then that. So we can see that this is our hypothesis, x and y are odd, and this is our conclusion. We're trying to prove that x times y is odd. So that'll help us state our assumptions and state what we're trying to prove. Okay, so we should always start out by stating our assumptions. So I would say assume that x and y are arbitrary odd integers. Okay, state my assumption. Then I probably would like to tell you where I'm going with this thing. So we will show that the product of x, y is also odd. Okay. So now the reader knows that's what we're trying to get to, and as soon as I see that, I'm done. Okay. So I know from my assumptions now I have to work off of my assumptions and use only valid arguments to somehow get to this point that x, y is odd. So my assumptions were that x and y were arbitrary integers. Okay, well I know the definition of odd. Usually that's the first place I'm going to start. Okay, so by the definition of odd, we know there are integers a and b such that, so x equals 2a plus 1 and y equals 2b plus 1. Okay. So one thing you'll notice that I did last time and this time, when I do math, I like to kind of like indent it and let's have it line up. So put, the English sentences, I kind of line up left justified, and the math part. So you could kind of just follow the math, and the words are kind of the fluff filler that are helping you the flow. Okay. Sometimes you can label the equations if you need to as well, like 1, 2, then if you want to refer to them later. Okay. All right, and so we know we need to prove something about the product. Okay. Okay, so you might say then x, y is, okay, x, y equals, well, that would be 2a plus 1 and 2b plus 1. And now you probably need to do a little math to figure that out. So let's see, we're going to get 4ab plus 2a plus 2b plus 1. And then always keep in mind where I'm going. Where am I going? I'm trying to show that xy is odd. Okay, so here's xy, and I have an expression for xy, and I'm trying to get that it's odd. So we know, remember, the definition of odd is that I can take 2 times some integer plus 1, and if I can put it in that form, then it's odd. Okay, so I have this really juicy plus 1 sitting right out there, and if I could just turn the rest of it into 2 times something, it would be great. So can I do that? Yeah, so if I just factor a 2 out of this first part and just leave that 1 hanging out, I would have 2 times 2ab plus a plus b. Okay, it's written just in that nice form. So as long as I can just show that this thing is an integer, it'll meet the definition that I need. So let's just say let k equal 2ab plus a plus b. Okay. So we only have multiplication and addition here. So since the set of integers is closed under multiplication and addition, you can abbreviate. If we were typing it, we could type it all out, but it's long to write. Okay. That means k has to be in the set of integers. Okay. So then we have that xy equals 2 times k plus 1. And by definition of odd, xy is odd. Or you could just say by definition, xy is odd. Okay, that's exactly what we set out to prove. We said we were going to show that xy is odd. We just did show that xy is odd. So that would be the end of it. Yes?
Do we have to prove that k was an integer? Because in the odd definition, it's only true when k is an integer.
Yeah, so k, yeah, we did right here.
Yeah. What I was asking is that why we had to prove
Yeah, that's why we had to, because in the definition it says if there has to be an integer. Yeah, so the definition says that, x is odd if there exists an integer k such that x equals 2k plus 1. Yeah. And then when we were showing that things weren't odd, it's because you would have to, the only k that you could come up with was like, 2/3 or something like it. Just if there's a rational number that's not an integer, it's not odd. So you have to show, you have to argue that it's an integer. Otherwise it doesn't meet the definition. Good question. Any other questions on that one? Okay. So let's do one with rational numbers. So this might be the last one we have time to do. All right, prove that if x and y are rational numbers, then 3x minus 2y is also a rational number. Okay, so this one is pretty easy to see that this is our hypothesis and that this is our conclusion. Okay, so we're going to assume x and y are arbitrary rational numbers. Okay. And then we'll show that 3x minus 2y is also rational. All right, so it's important that we know the definition of rational. So by definition of rational, there are integers, I'll call them a, b, c, and d. Okay, so x has to be able to be written as a ratio of 2 integers, and y has to be able to be written as a ratio of 2 integers, and the denominators in both of those can't be 0. So I'll have x, okay, be a over b. So I have to put on here that b can't be 0. And I'll write y as c over d. And so I have to put here that d is not equal to 0. Okay. So the definition says, if x is rational, I can find two integers whose ratio is x, and then one that's in the denominator can't be 0. Similar for y, there are two integers whose ratio is y, and the denominator can't be 0. Okay. Substituting these expressions into 3x minus 2y gives us, that 3x minus 2y equals 3 times, x is really a over b, minus 2, and y is really c over d. Okay. And now our goal is to show that that is a rational number. Okay, well, if it is a rational number, then we need to be able to write it as a ratio of an integer over an integer. Okay, so essentially, if I could turn this into a single fraction, so let me rewrite this as like 3a over b minus 2c over d. Okay, so if I went and I multiplied this one by d over d, and I multiplied this one by b over b. I'm just using the identity property of multiplication. It's an algebraic property. I'm multiplying things by 1, haven't changed anything. If I do that, then I now have a common denominator of bd and a numerator of 3ad minus 2bc. And so I've now written it as a ratio. And again, I just have to argue that it is a ratio of integers. Okay, so let's see. I'm just going to say closure properties of integers. 3ad minus 2bc is an integer, and bd is also an integer. Okay, so this one uses subtraction and multiplication. This one just uses multiplication. You could list them out, multiplication and subtraction, or you could just say closure properties and you kind of cover all your bases. Okay. And so, thus, by definition, 3x minus 2y is rational. Okay, that's what I set out to prove, and so I'm done. Good, do you think you could do it if you had to? Okay. Yeah, we'll practice more next time. Okay.